Welcome back to another lesson on A-level physics. Today's learning intention is to solve problems using radians, and this is the first lesson on circular motion. Success criteria for today is to convert between degrees and radians, to distinguish between centripetal and centrifugal force, and to explain practical examples of centripetal force. Let's dive straight in with a task to introduce the topic of circular motion. I would like you to think back to the studies that we've done on Newtonian mechanics and give me the definition and the units for acceleration. And then a car can accelerate by either speeding up or slowing down. Are there any other situations which a car can accelerate in? Pause the video, answer the questions, and then press play to mark your answers. So the definition of acceleration is that it is the rate of change of velocity. Don't say change of velocity, it is the rate of change of velocity. The units for acceleration, because we're doing velocity divided by time, that is meters per second divided by seconds, giving us a unit of acceleration that is meters per second squared. And then finally, I've told you in the question that a car can speed up or slow down to accelerate, but are there any other situation which a car can accelerate? Yes, there is. You might remember studying this at GCSE. If a car moves round a bend or moves in a circle, then we can also say that it is accelerating even if it is moving at a steady speed. This is because velocity, of course, is a vector. Vectors take into account direction, so when the car moves in a circle, its direction changes, and so therefore its velocity is also changing. Okay, now obviously acceleration in terms of speeding up is calculated by doing the change in velocity divided by time, but we also need a way of calculating the acceleration caused by moving in a circle, which is of course what we call the centripetal acceleration. Now, centripetal acceleration has a formula which is given below as acceleration, or centripetal acceleration is the linear velocity squared divided by the radius of the circular motion. Now, in order to actually go round in a circle, the resultant force on the object cannot be zero because obviously there is a change in velocity going on and forces cause acceleration. The force that causes centripetal acceleration we refer to as being centripetal force. Now, we know that resultant force from Newton's second law can be given as force is mass times acceleration, and because acceleration centripetally is v squared over r, we can say that the equation for centripetal force comes out, of course, as being mv squared divided by r. Okay, now let's look at a situation, any situation where there is circular motion going on, there has to be a centripetal force. Now, centripetal force always acts towards the centre of the circle. So in this situation of the toy train moving around a circular path, the centripetal force acts towards the centre. Now, centripetal force isn't a force in its own right. What centripetal force is the umbrella term for any force that causes circular motion. Now, in this situation, if we look at the actual wheels of the train going around the track, obviously the wheels are touching the rails. Now, because the outer rail is capable of pushing inwards on the train towards the centre of the circle, that means that the normal contact force between the outer rail and the wheel is what is providing the centripetal force in that situation. Of course, the inner rail would have to push outwards on those wheels, and so that can't provide the centripetal force. Now, there are lots and lots of other examples in physics and real life of centripetal forces. For example, the Earth goes around the Sun in sort of a circle, and that is caused by gravity, so gravity can be a centripetal force. Likewise, an electron moving around the nucleus of an atom, that is caused by an electrostatic force, and so electrostatic forces can be centripetal forces as well. Now then, I've used the phrase already once in this video, linear speed, but let's go into that in slightly more detail. When an object moves in a straight line, we know that we're capable of working out its speed using the equation speed is distance divided by time. That you've probably been doing since Key Stage 3. But what we would determine that speed as is being the linear speed, because it is the speed when you're moving in one direction. Now, there is obviously a slightly more complicated situation when we consider an object that is moving in a circular path. Because if an object is moving in a circular path, at any given instant, it is moving linearly at a tangent to that circle. Now we can work out what the speed of that object is by just manipulating the equation speed is distance over time. We know that the distance all the way around a circle is 2 pi r because that is the circumference of a circle. So if we replace the distance with 2 pi r and we replace time with the time it takes to go around the circle once the time period, that tells us that the linear speed when we move in a circle is 2 pi r divided by t, where capital T is the period or the time it takes to go around the circle once. Now we can also work out what the frequency is. You'll remember from studying in waves that frequency is how many times per second. So in other words, the frequency of an object moving around a circular path is how many times it goes around the circle per second. Now the equation for frequency is 1 divided by time period, just as it is in the waves topic as well. And frequency, of course, is still going to be measured in units of Hz, hertz. Right, let's have a go at an example question together. A cyclist is travelling at a speed of 25 metres per second on a bicycle which has wheels of radius 750 millimetres. We want to calculate the time for one rotation of the wheel. Well, if we look at this information given to us in the question, we know the speed of the bike is 25 metres per second, which means that the wheels are moving at 25 metres per second as well. I also know the radius and I want to work out the time for one rotation. So I can start off from the fact that we've just said that speed is distance over time. In other words, v equals 2 pi r divided by t. Now, from there, it's just a case of rearranging for t. So I will multiply up by t and divide by v to give me time period is 2 pi r divided by v. I substitute my numbers in, but of course 750 millimetres needs to be put into standard units of metres, so that will be 0.75. So 2 pi times 0.75 divided by 25 will give me a time period of 0.19 seconds. We now want to work out the frequency of rotation of the wheel. The frequency is 1 divided by the time period, and so that will be 1 divided by 0.19, which gives 5.3 hertz. Please don't forget to include hertz on your answer line. Then part C, we want to work out the number of rotations of the wheel in 1 minute. So I know that the frequency is 5.3 hertz, so it goes around 5.3 times per second. And so if it's going around 5.3 times per second, I can multiply that by 60 to find out how many times it goes round per minute, and it does 316 rotations per minute. Okay, so in terms of working with angles, you're probably used to working with angles in degrees, and I know that you know from Key Stage 4 maths that in a circle there are of course 360 degrees. However, we're going to introduce the SI unit for angles, which is in fact radians. Now in a circle there are 2 pi radians. Now that can be written as 2 pi with a little c as a superscript, or it can be written as 2 pi rad, which is what I've gone for there. Now what I would like for you to do is to use that information to complete this table for me, please. So pause the video and convert each of these angles that are currently in degrees into radians, please. Okay, so 0 degrees is obviously still going to be 0 radians, no surprises there. Now we know that 360 degrees was 2 pi, so obviously if you did 360 divided by 4, you'd get 90, so 2 pi divided by 4 gives you pi over 2 radians. 180 degrees would be pi radians, and 360 degrees, I've already told you, is 2 pi radians. So some nice simple conversion practice for you there. Now let's look at the concept of angular displacement then. Angular displacement is the angle an object moving through a circle has turned through in a certain amount of time. Now what I've got for you in the diagram there is I've mapped out the path that an object moving in a circle has taken and shown the angle that it's been displaced by. So that angle theta we would say is the angular displacement. We can work out what that angle is using the formula theta is 2 pi t divided by capital T, where lowercase t is the time that the object has actually been moving for, and capital T is the time for one full rotation, otherwise known as the period. Please note that that equation is not given to you on the formula sheet and so needs to be learned. If it helps though, you will remember of course that when we looked at phase difference in the topic of waves, you've actually learned that formula already because it is still theta equals 2 pi t divided by capital T. Now let's go on to talk about angular speed then, because obviously if speed is the rate of change of displacement, then angular speed is the rate of change of the angular displacement for an object in circular motion. So if angular displacement is 2 pi t divided by t, we would divide that by t to find out what the angular speed is, and of course that would therefore come out as being angular speed is 2 pi divided by the time period. We're using that symbol there which looks like an italic W, but it's actually omega. So omega equals 2 pi divided by period. Now the units for angular speed are going to be radians per second, which we would write down rad s to the minus 1. Let's look at a second example. A cyclist is travelling at a speed of 12 metres per second on a bicycle which has wheels of radius 0.4 metres. Calculate the frequency of rotation of the wheels. Well, to work out the frequency, we first of all need to know what the period of the wheels are. So I use the equation for speed, which is distance over time, 2 pi r being the circumference of a circle, of course, and I rearrange that for period to get 2 pi times 0.4 divided by 12, which gives 0.209 seconds as the period. Now frequency is 1 over the period, so I would do 1 divided by 0.209, which gives 4.8 hertz. And I want to work out the angular speed of the wheels. Now the angular speed is given to you on the formula sheet. It is omega equals 2 pi divided by t. So you would do 2 pi divided by 0.209, which comes out as 30 radians per second. Please include the unit rad s to the minus 1. Now I want to work out the angle that each wheel has turned through in 0.1 second in units of radians. So that is of course asking us to work out angular displacement. The equation for angular displacement is 2 pi t divided by t. So I just substitute in 0.1 because that is the time that it has been moving for. The period is 0.209 and so that will come out as 3 radians. But it now wants me to work this out in terms of degrees as well. And because we know that there's 2 pi radians in a circle, which is equivalent to 360 degrees, I can just manipulate that formula for angular displacement to become 360 t over t, because obviously 360 degrees is equivalent to 2 pi radians, and then I substitute in the same data, so it's 360 times 0.1 divided by 0.209, which gives me an answer of 172 degrees. Okay, I would like to have a go at the following task for me, please, which is to do with an application of circular motion. Automatic brakes are used to prevent lifeboats from falling freely when lowering them into the sea. The diagram shows a cross-section of an automatic brake fitted to a rotating shaft. The brake pads are held onto the shaft by springs, which you can see by the zoomed-in section of Figure 1. Two parts of the task. I want you to explain why the brake pads will press against the inner surface of the stationary collar if the shaft starts to rotate too quickly, and I would like you to explain the effects on the system if the springs become too weak. Pause the video. I would expect this to be a 6-mark question on the exam, so please go into a lot of detail with your writing, please. So, to answer this question then, for the brake pads to actually move in the circular path that they're meant to, there needs to be a centripetal force acting on them, and that is being provided by the tension in the springs. So you can have 1 mark if you've said that tension in the springs provides a centripetal force. Now, as the shaft rotates faster, the brake pads will also rotate faster, but that means that a bigger centripetal force is needed to act on them. That is because force is mass times velocity squared divided by the radius of the circle. So because they're moving faster, a bigger centripetal force is needed. So the second mark, in short, is for saying the faster the rotation, the bigger the centripetal force needs to be. A third mark for saying that that means that the tension in the springs therefore needs to increase. Now, as the tension gets bigger, that means that the springs are actually going to extend, and you will remember that from the materials topic that we did right back in September, where Hooke's law says that the force on a spring is equal to the spring constant multiplied by its extension. So because the force has gotten bigger, the extension of the springs increases as well. You will get a mark for stating that. Then finally, it says explain the effect on the system if the springs become too weak. Well, if they become too weak, then that means that their spring constant is going to be reduced. And so therefore, at a certain speed of rotation, the extension of the springs will be larger for weaker springs. And so that means that the brakes are going to touch the collar earlier, and so therefore friction acts earlier, so the boats will be lowered much slower than they would be meant to. Okay, what I would like you to do for me now, folks, is have a go at both of these sections of questions. The first questions are grade B and C, and then the final green set of questions are a little bit more demanding at grade A. Question 1. Calculate the angular displacement in radians of the tip of the minute hand of a clock in 1 second, 1 minute and 1 hour. Now, if you visualise a typical clock, of course the minute hand takes an hour to go all the way around because there are 60 minutes in 1 hour. So, to work out the angular displacement then, of course we're going to use the equation that we needed to learn. The angular displacement is 2 pi t divided by t. And then, of course, if the time is 1 second, then 2 pi times t is just 2 pi. And then we divide that by the period of rotation. The period of rotation, of course, being 3,600 seconds, because that is 1 hour. 2 pi divided by 3,600 comes out as 1.75 times 10 to the minus 3 radians. Part B. Very similar thing, we use the same equation, but then this time, of course, in 1 minute, the value of time is 60 seconds, so we do 2 pi multiplied by 60 divided by the period of an hour, which is 0.1 radians. And then for part C, again, we're using theta equals 2 pi t over t, but then this time, the value of time that it's been moving for is 3,600, the period is 3,600, so they cancel out to give us a displacement of 2 pi radians. Question 2. An electric motor turns at a frequency of 50 Hz. Calculate the time period. Well, we know that frequency is 1 over time period, so time period is also 1 over frequency, so we do 1 over 50, which comes out as 0.02 seconds. Then for part B, we want to work out the angle that it turns through in radians after 1 millisecond. So to do that, we're going to use theta is 2 pi t over t. 1 millisecond is, of course, 0.001 seconds. The time period we've just worked out is 0.02, so that gives us an angular displacement of 0.31 radians. We then do the same procedure, but look at how far it's turned after 1 second. So again, we use theta is 2 pi t over t, but then it's 2 pi times 1 divided by 0.02, which is 100 pi. Question 3. The wheel of the London Eye has a diameter of 130 metres and takes 30 minutes for a full rotation. Calculate the speed of the capsule. So we've been given its diameter and its period. A little bit of manipulation needed because the diameter needs to be halved to give us the radius, and we need to put the time period into seconds, but it's not too much of a problem. We use v equals 2 pi r over t, so 2 pi times 65 divided by 30 times 60 gives us 0.23 metres per second. We then want to work out the centripetal acceleration of the capsule. Remember, at the start of the lesson I defined centripetal acceleration as being v squared over r, so we do 0.23 squared divided by 65, which gives 8.1 times 10 to the minus 4 metres per second squared. Centripetal acceleration, of course, has the same units as linear acceleration. Then finally, we want the centripetal force. Centripetal force, F equals mv squared over r. So the mass is 65, times that by 0.23 squared, and then divide by 65. That gives us 0.053 newtons. Question number 4. You might see this done as a practical at some stage. A string passes through a smooth, thin tube. Masses M and capital M are attached to the ends of the string as shown. The tube is moved so that the mass M travels in a horizontal circle of radius r and at a constant speed of v. And we want to express capital M in terms of lowercase m, g R and V. Now to do this, we've got to think about what is going on. That smaller mass M is moving in a horizontal circle. Because it's moving in a circle, there must be a centripetal force acting on it, and we know that centripetal force is given by mv squared over r. So the centripetal force on that small mass is v squared divided by r. Now, the thing that provides mv squared over r in that case has to be the tension in the string. The tension in the string has to counteract the weight of that larger mass. The weight of that larger mass is capital Mg. So what we can actually see is that Mg is equal to mv squared over r. Now, I wanted to express m in terms of mg, r and v, so I simply divide by g to get capital M is equal to mv squared over gr. Now let's move on to the grade A questions. 1A. Calculate the rotational frequency of the Earth due to its daily rotation on its axis. No numbers were given in the question, but if you think about it, the Earth will rotate once every 24 hours. So we actually do know what the period of rotation is. It's 24 hours, and we can convert that into seconds by doing 60 times 60 times 24. We then do 1 over the period, which gives us the frequency of 1.16 times 10 to the minus 5 Hertz. We then work out the angular velocity of the Earth due to its rotation using omega equals 2 pi over t, or you can do omega equals 2 pi f if you prefer. Doing the 2 pi over t method, you would do 2 pi divided by 60 times 24, which gives 7.27 times 10 to the minus 5 radians per second. The working out that I've put on the board is 2 pi f, so we just multiply it by the frequency instead to get the same answer. Then for part C, it says finally calculate the linear speed of a point on the equator given that the radius of the Earth is 6.4 times 10 to the 6 metres. So if we're on the equator, then that means that we are moving in a circle that is equal in radius to the radius of the Earth. So we simply do V equals 2 pi r over t, 2 pi times 6.4 times 10 to the 6 divided by 60 times 24 gives 465 metres per second. Question 2. A satellite in circular orbit of radius 8,000 kilometres takes 120 minutes to orbit. Calculate its speed. So again, we know what the radius is and we know what the time period is. So to work out the speed, we do 2 pi r divided by t. Remember, 8,000 kilometres should be written as 8 times 10 to the power of 6 metres. And we divide that by the period. We don't work in minutes, we work in seconds. So 60 times 120 gives us the period in seconds. That comes out with a speed of 7 kilometres per second, or 7 times 10 to the 3 metres per second. We then want to work out the angular displacement after 1 second, so we use theta equals 2 pi t over t. Substituting values in, lowercase t is 1 because we're talking 1 second, and the time period we've just worked out as being 60 times 120. That gives an angular displacement of 8.73 times 10 to the minus 4 radians. If we then do the same question in degrees, we can just replace 2 pi with 360. So we do 360 divided by 60 times 120, which gives 0.05 degrees. Final question. A hammer thrower whirls a 2 kilogram hammer on the end of a rope in a circle of radius 0.8 metres. The hammer took 0.6 seconds to make one full rotation just before it was released. Calculate the speed of the hammer just before it was released. So again, similar to all the questions that we've done today, we're using V equals 2 pi r over t, 2 pi times the radius, which was 0.8, divided by the period, which was given as 0.6 seconds, comes out with a linear speed of 8.4 metres per second. We then work out the centripetal acceleration using v squared over r, so we do 8.4 squared over 0.8, which comes out as 87.7 metres per second squared. Please focus on including the units for that in your answer. And then for part C, we wanted to work out the centripetal force. Centripetal force is, of course, mv squared over r. I know that the mass of the hammer is 2, so we do 2 times 8.4 squared divided by 0.8, which is 175.5 newtons.